Welcome to our another online session for the course Computer Organization, and this session is designed for the students of BEE7A. In the previous session, we were discussing about the processor design, specifically the single cycle processor design we were discussing, and we've discussed about how the R format instructions and other instructions, I format instructions, and load word and store word and branches are implemented on single cycle processor. And we have also discussed about the components that are being involved in the single cycle processor. For example, the sequential elements, the processor design, in the processor design, the control unit, and what is the functionality of the control unit, and how control unit manages and controls the data path. We have discussed that in detail. And we have also discussed the limitations, not in detail, but in general, that the performance is limited by the longest instruction, and the clock cycle time is determined by the performance of the longest instruction. That is, in our case, the load word instruction. And we have to set the clock cycle time according to the slowest instruction, and the slowest instruction determines the critical path of the system, and we have to find the critical path. In the previous session, we have discussed about the branch equal instruction, how we implement the branch equal instruction in detail. While discussing about the branch equal instruction, we have seen that how the functionality is achieved by using the single cycle processor. In today's session, we will be discussing the jump instructions, how we'll implement the jump instruction in detail. But before going to the jump instruction, let us modify the same data path for branch not equal instructions, and let us see what are the changes that are going to be happen while implementing the branch not equal instruction, other than the branch equal instruction. So if you see the format of the instruction, that is BNE, branch not equal, dollar sign V1, comma, dollar sign V2, and we've got a label. Branch not equal instruction is also the conditional instruction, and that would work in the same way, but now the condition that has been tested is the not equality condition. And now what would be the possible value of the program counter, because we are reacting in the opposite way as compared to the branch equal instructions. So we can see the possible values of the uh, program counter. In case if we got no branches, then it should be implemented as PC plus 4. If you got branches, then we've got two cases, case 1 and case 2. Case 1, when the condition goes false, which means that dollar sign V1 was equal to dollar sign V2. In that case, the condition is false. If V1 is equal to V2, in that particular scenario, if equality holds, then this is the false path for branch not equal. And if V1 is not equal to V2, this is the true case. So in false case, we would use PC plus 4 to update the program counter. But if condition got true, then we have to add PC plus 4 plus label. Now what would be the status of the zero flag? If V1 is equal to V2, then zero flag is set. So that represents the false condition, and if zero flag has the value 0, that represents the true condition. Now how we're going to incorporate that? We'll see that. First of all, we fetch the instruction from the instruction memory. Read V1 and V2 at read data 1 and read data 2. At read data 1, we are getting dollar sign V1, and at read data 2, we are getting dollar sign V2. And at the same time, what we are doing is that we are sign extending the label part. If in case the condition gets true, then multiplying with 4 and then adding with PC plus 4. This part we are doing at the same time. So we should have both values ready in case of true or in case of false. Each condition should be met. So here ALU will subtract V1 and V2 from V1, and then resets the zero flag. Now in this particular scenario, we've got a branch signal. Definitely this signal will get high if there is a branch instruction, either it's branch equal or branch not equal instruction in this particular case. But now the zero flag will decide that what would happen if we have the same circuit as branch not equal. Then the condition is reversed basically, and we are operating in a reverse direction. So what we have to do is we have to invert this zero flag, and we've used an inverter, a NOT gate here. Now let us execute this. If there is no branch, for example, the first case, we are discussing about the first case. If there is no branch, then this branch is equal to 0, and whatsoever the status of zero flag is, don't have any concern with that. So in that case, PC plus 4 is uploaded. If you see that this PC plus 4 will upload it into the program counter, so it is working fine. Right, so now assume that we have a branch instruction. So in that particular scenario, the branch signal would be 1, and then the zero flag will basically decide what would be loaded to the program counter. And if zero flag is set to 0, definitely the contents were not equal. That is a true condition. We have to invert that in order to select PC plus 4 plus label, and in that way PC plus 4 plus label is assigned to the program counter. Now let us see how we're going to implement the jump instruction, the unconditional jump instruction basically. And if you see the format of the instruction here, so first 6 bits represents the opcode here. This is the opcode, and opcode value is 2 for the jump instruction. And remaining 26 bits, these are the 26 bits, represents the jump address. So what we have to do is, if we encounter the jump instruction, definitely that will change the sequential flow of execution. We are not going to check any condition for that. So what we have to do is we have to assign the program counter the jump address. Now what would be the jump address? Would it be these 26 bits, or do we have to manipulate these 26 bits in order to generate a jump address? Because program counter is a 32-bit register and these are 26 bits. So what we have to do is, definitely this is a memory address. First of all, we have to multiply 4 with it. So multiplying the 4 with it will make these bits 28, because we are left shifting the data by the factor of 2. So these 26 bits are converted into 28 bits, and the rest of the 4 bits we simply just concatenate the program counter most significant nibble with the address. So what we would do is we would basically use jump address and update the program counter with concatenation of 4 bits of old program counter relative to that we are making the jump, and 26 bit of jump address, and definitely with 2 left shifted we have to add 2 zeros to make it 28. And we have to need an extra control from the control unit that would be enabled in the scenario whenever there is a jump instruction. Same in a way we have introduced the branch signal that is enabled when there is a branch in the system, right? Now let us see the data path, and we'll see how the system will be implemented. And jump instruction is the shortest instruction and the fastest instruction as compared to the other instructions. But due to the single cycle, we have to bear the penalty of the wastage time due to the critical path. So we just only have to fetch the instruction, and we don't have to do anything else. So we don't need any register content. So in that particular scenario, no register file is used, no ALU is used, no data memory is used, and no register file again is used. So this is the fastest instruction, and in that particular scenario, when we fetch the jump instruction, we've got the machine code here, 32-bit machine code. We have applied the opcode to the control unit, and whenever control unit sees that it's a jump instruction, control unit will set this jump equals to 1. All right, and now what we have to do is we have to extract those 26 bits and then convert them into 28 bits, and then we have to concatenate that. So what we have done here, if you see that we are using this line, these are the 26 bit of the address multiplied by 4. So we are using shift left 2, that are converted into 28 bits, and here we are taking the most significant nibble of PC plus 4 and concatenating it in a circuit. So definitely this is not the direct connection the circuit suggests. It's basically a concatenation operation here. So what we are doing is we are simply concatenating the uh, four most significant. We are simply assigning the jump address four most significant bits and connecting that with program counter four more significant bits. We are just making the interconnection. So this diagram doesn't mean that the whole PC plus 4 that is 32 bits is concatenated with the jump address. So we are only taking the most significant nibble here, and we are just replacing that with the jump address most significant 4 bits. So this is the jump address that is ready now. So when we have to assign the jump address whenever the jump equals to 1. So if you see that this jump equals to 1, so in that particular scenario jump address will be assigned to program counter, or otherwise and the other possibilities that can be PC plus 4 or PC plus 4 plus label in other instructions that can be assigned to the program counter. Well, with this, we have discussed almost all the scenarios and all the instructions that can be implemented in a single cycle processor, and we've seen the possible modification in the single cycle processor. So that was all for the single cycle processor. Now onward, we would move to the pipeline processor. So what are the limitations in the single cycle processor? There are some performance issues which we have discussed that informally before discussing that. Because the most critical thing is that the longest delay determines the clock period. What does that mean? It means that the critical path basically is determined upon the slowest instruction or the longest combinational path that exists in a circuit. So we have to set the clock cycle time equal to that, because if we set the clock cycle time lower to that, some of the instructions have possibility to be executed, but not all the instructions. So we have to select the clock cycle time in such a way that all of the instructions are executed simultaneously. So which instruction will be affected mostly? The jump instruction will be affected mostly, because jump instruction only requires the first process. So the rest of the time is just wasted in that particular scenario. So our critical path is basically the load instruction. That is the longest instruction that consumes fetch section, decode section, execution portion, data memory portion, and again back to the register file. So that is the longest. So we can see that we've used instruction memory, then again register file, then ALU, then data memory, and then again register file. So the delays of all the functional units will be added while determining the time for the load instruction. So it's not feasible to vary period for different instructions, which are we have said that if we vary the period of the different instructions, then some of the instructions get executed and some of the instructions won't get executed. So it basically violates the design principle. So uh, we have to make the common case fast, basically by making the common case fast. So we will improve performance by pipelining, basically, and we will see how we will improve the performance by pipelining by first defining what the pipelining is and how we're going to implement the pipelining, so that we can execute the instructions not in a sequential order, but we can overlap the execution of instructions, and we can change the clock cycle time depending upon the slowest stage rather than the slowest instruction or the critical path of the system. Now, how we're going to achieve that? We have to introduce some sequential elements in our design, and we will see that how the sequential elements in the design are added, and what is the maximum limit that we can add in our design, the sequential components, so that our performance won't be compromised. Well, student, that was all for this session, and in the next session we will start with pipelining and basic principles of pipelining, and we will see the challenges that we can, if we are improving the speed up, we are improving the throughput, then what are the challenges depending upon the latency of the instruction and how the performance is related to that. Till then, take care. Have a good day.